We want to answer the question, when is Galois group of a polynomial equal to the symmetric group or group of permutations? So where P is our prime, so P is some prime number. So again, recall SP would just permute the letters or integers 1, 2, 3 all the way to P. So we start with the irreducible polynomial over rational. So f is a irreducible polynomial and degree of f is P. So this first sentence immediately tells you that our Galois group is a subgroup of group of permutations. Now if f splits in complex numbers and has exactly two non-real roots, so it has exactly two non-real roots, then the Galois group of the polynomial is equal to the symmetric group. So let us see an example before we discuss the proof. So say your f of x is given as x to the power of 5 minus 4x plus 2 over rationals, and you can check it is irreducible by Eisenstein's criterion. Now since this is a polynomial, we can use Rolle's theorem, and Rolle's theorem says that between two roots we will have the derivative equals to 0. So pictorially this is how it looks like. So this is our x-axis, this is our graph of our polynomial, say, and so between two roots, so say this is root 1 and then you have another root here, root 2, you will have a derivative which will vanish. So if this is graph of f, you will have f prime is equal to 0. So this is what is all Rolle's theorem is. You take the derivative of this polynomial, you immediately get 5x4 minus 4. So you can see that this has only two real roots. So there are only 2 points at which f prime would vanish. So say f prime vanishes here and then f prime vanishes here. So this would mean that there are at most 3 real roots. So by Rolle's theorem, this f prime is equal to 0 between two real roots. So these have 2 of them f prime are 0, so the third real root is here. So you can see pictorially there are at most 3 real roots, because this could have, rather than going up, it could have an inflection point, it would have gone down. So at most 3 real roots. So we have at most 3 real roots, because it could have an inflection point and this could have gone down rather than going up. Now we use the intermediate value theorem. So intermediate value theorem will say that we have at least 3 roots, and then you will have exactly 3 roots. So again, you plug minus 2 in here, you get minus 22. You plug 0 in here, you get 2. So obviously this is a continuous function, so this will cross the x-axis at some point in time between minus 2 and 0. So there is one real root between minus 2 and 0. So there is one root here, and then between 0 and 1, this is positive at 0 and negative at 1. So it crosses x-axis between some interval between 0 and 1. So there is one root right here, and then obviously 1 is negative and 2 is positive. So in the interval 1 to 2, there is another real root. So there is another real root here. So there are at least 3 real roots by intermediate value theorem, and there are at most 3 real roots by Rolle's theorem. So f has precisely 3 real roots, and since it is irreducible of degree 5, therefore it has 2 complex roots. So now use this theorem. So f splits in complex with exactly 2 non-real roots, so 2 complex roots, and therefore g of f is sp, where p is the degree of the polynomial. So g of f is s5 because 5 is the degree of the polynomial. Now this is a very, very important example. So if you're seeing this lecture, you should memorize this example by heart, because this will again show up while we prove insolvability of the quintic. So such a polynomial is insolvable, and we are going to use this result again there. So now we're going to prove this result. So for this we are going to use 2 important facts. The first fact is this SP, that is group of permutations on p integers with p prime. This is generated by a p cycle and a 2 cycle. So again, recall that SP, it just acts on this group, this integers, it permutes them, and a p cycle would contain all of these integers. They will be jumbled up in some way, but since the p cycle, it will contain all of them. So a p cycle and a 2 cycle, which is just a transposition, these two elements, this element and this element, they will generate entire SP. And the second fact we are going to use is that if p is a prime number and it divides order of a group, then the group contains an element of order p. So it contains an element of order p. So let us start with the proof. So say E is a splitting field of f and alpha is root of f. Then you adjoin alpha to rationals, then degree of this extension is degree of f, which is p. So given to us that degree of f is prime p. So therefore p divides this degree of extension E over q, precisely because E over q is E over q alpha and q alpha over q, and this part is precisely equal to p. So p divides this. Now this would imply that p divides the order of the Galois group, because the Galois group order is precisely the degree of extension. So therefore Galois group contains an element of order p. So Galois group contains an element of order p. So we already know that the Galois group is a subgroup of SP, because it will just permute the roots of this polynomial of degree p. But the only elements of order p in SP are p cycles. So only elements of order p in SP are p cycles. So our Galois group now contains p cycles, because whatever element you have in the Galois group will also be an element of SP. And if you have an element of order p in Galois group, it will also be an element of order p in SP, and therefore you have these p cycles here. So p cycles are contained in our Galois group. Now say let tau be a complex conjugation in complex numbers. So you recall that roots, they come in pairs. So if a complex root satisfies an equation, then its conjugate also satisfies the equation. So if tau is a complex conjugation, then it is a 2 cycle. So it's a 2 cycle because it just exchanges the two roots which are conjugate of each other. So it simply interchanges the conjugate complex roots and fixes everything else. So thus GF also contains a 2 cycle. So it contains a 2 cycle and it contains a p cycle. And therefore it has all of SP, because p cycle and a 2 cycle will generate SP, and the Galois group is already a subgroup. Now we have shown that it contains both the elements which generate SP, so it generates the entire permutation group. And that is what we wanted to show. So if f splits in complex numbers and it has two non-real roots, then the transposition will change these two real roots, and therefore the Galois group has a 2 cycle, and it already has a p cycle because of this prime p here, and therefore g of f is SP. The proposition does not hold in the other direction. So that is, there are polynomials with real roots which can have a Galois group which is SP. For example, you have this polynomial x5 minus 5x cubed plus 4x minus 1. It has all real roots and its Galois group is S5. So it is not necessary that the polynomial has to have complex roots to have SP, but this criteria is important because you can construct easy examples. But this shows that converse doesn't hold.